Welcome to Online Algebra 2. This is section 5-4, Dividing Polynomials. So our objective for this section is to divide polynomials using long division and to divide polynomials using synthetic division. And what you should know is that you can divide polynomials using the steps that are similar to the long division steps that you would use to divide whole numbers. So let's go back a little bit and recall the long division algorithm. Okay, so when we want to do long division back in grade school, we had a couple steps. The first step was to divide. So with 3, we couldn't go into 1, so we would go into 10, and it goes in 3 times. The second step was to multiply. So 3 times 3 gave me 9. Then we subtract. So we did 10 minus 9 to give me 1. And then bring down this number right there to 1. And then the last step is to repeat. And you just keep repeating until you get to the end. So divide, multiply, subtract. Now there's nothing to bring down here. So that means that 101, there's a remainder. There's something left over at the end. Now we could, with numbers, put a decimal and start, keep going like this. So polynomials, we're not going to do that. We're just going to list the remainder, and we're not going to put a little r for remainder. We're going to list it as a fraction, the remainder over the divisor. Okay, and that was the long division algorithm. Divide, multiply, subtract, bring down, and then repeat. So when you try to factor a polynomial, right, we're still doing the same thing that we just did with whole numbers. Is you're trying to find a divisor of the polynomial that gives you a quotient and a remainder of 0. And this suggests that being able to divide one polynomial by another could help you maybe factor the polynomials. And again, here's an example with numerical long division that actually does work out. So you would divide 21 into 67 is 3, multiply, subtract, bring down the 2, divide, multiply, subtract, and then you have a 0 as a remainder. Now look at the steps with similar numbers, right? We have a 6x squared, a 7x, and a 2 with this polynomial, okay? So now we're going to divide the polynomial 2x into the 6x squared. We get 3x. Multiply to get here, subtract, bring down the 2, and we're going to look at this in similar ways with the numerical long division. And the remainder from both of these is 0. So that means 21 is a factor of 672 as well as 32. And it also means that 2x plus 1 is a factor of the 6x squared plus 7x plus 2, as well as 3x plus 2 is the other factor. Let's try this. Let's use long division to divide these two polynomials and see what happens. Okay, so we're going to start like this. X plus 5. I'm going to put my division 4x squared plus 23x minus 16. Now, it is important for both of these terms to be in standard form. That means biggest exponent to smallest. Okay? You are going to use the lead terms to do the division step. Okay? So basically what we're going to be doing is taking 4x squared, divide by x to give me 4x, right? 4x squared divided by x, right? One of the x's cancel, and we're left with just 4x. Now, don't put it there, okay? Better for us to write it above the term with the same degree. So I'm going to put it there because both of these are the same degree. And what that does is it lets us keep putting in terms in the top, in the quotient here, until I get to the end. All right, so that's my first step, was divide. Next step is multiply. I'm going to now this 5 comes into play, because I'm going to take the 4x and I'm going to multiply by both of these two. So we get 4x squared plus 20x. And then I'm going to subtract, okay? And we are going to subtract everything, which is why I put the parentheses. And the way I like to do this when I want to subtract is, I think the parentheses can be a little confusing. I just put a negative there, and then I change the sign of every single term, okay? Because you are subtracting all of these, so you need to subtract everything. These two cancel. That was the point, okay? Was to make those two go away. 23 minus 20 gives me 3x. Bring down the 16. Okay? Then repeat. Then do it all again. 3x divided by just the x. Don't worry about the 5 for now. 3x divided by the x gives me a positive 3. Multiply 3x plus 15. Subtract. So this cancels. This is 16. Negative 16 minus 15 is negative 31. There is nothing left. That means that we are finished. So that means the quotient is 4x plus 3. The top. The remainder is negative 31. If I'm going to write this answer as a polynomial, it would be 4x plus 3 minus 31 over the divisor x plus 5. Okay. Now, this also means that x plus 5 is not a factor of 4x squared plus 23x minus 16 because it had a remainder. Okay. So if you can't tell where we're going with this yet, is that sometimes quadratics we could always factor. We could always see if they have two factors, and if not, we use the quadratic formula. But when we had cubics or fourth power quartics, it was hard to factor them. So it would be nice to have an easy way to see if something's a factor, and this is the first step in that process. Let's try this one. And let's use long division. There is a simpler way, and we'll get to that in a second, but let's start with this for now. 3x squared minus 29x plus 56. 3x squared divided by x is 3x. Multiply 3x squared minus 21x. When I subtract, I'm going to change that now to a plus. So that turns into a negative 8x plus 56. And negative 8x there. Negative 8 times negative 7 is a positive 56. And now when I subtract, I get 0. So that means this has no remainder. That means x minus 7 is a factor of 3x squared minus 29x plus 56. And the other factor is 3x minus 8. Okay, so to refresh our memory a little bit about how division actually works, is that if you can divide a polynomial, p, by a divisor to get a quotient and a remainder, the equation for this, if the remainder is 0, then the polynomial is equal to the two things multiplied together, d and q, d of x and q of x, and they're both factors. If the remainder is not 0, then it's just d times q plus the remainder. Now, one thing to note is that to use long division, p of x and d of x should be in standard form with 0 coefficients where appropriate. Okay? And you keep the division process going until the degree of the remainder is less than the degree of the divisor. Or I reach the end, right? The degree here is 0, the divisor here is 1. I can't go any further. This step, right, they're the same, so I can do it one more time. Okay? Now this point right here, 0 coefficients. This is very, very important. That means is if a degree skips in the problem, you need to put in a 0 for that term. What do I mean by that? Just like this. Is x squared plus 1 a factor of this polynomial? Now, automatically, you should recognize that in standard form, this is missing an x term as well as this. Now, I don't just want to put another x into both of these because that would change the expression. What I do is put in 0 x's plus 1. And this becomes a placeholder. And it makes it so all the numbers line up correctly. Plus 12x squared plus 0x plus 5. Okay? And watch what happens when we get to this a little bit. So the rest of the process is pretty much the same. 3x to the fourth divided by x squared is 3x squared. And I'm going to write that right there. Now, if I didn't put this 0, okay, when I multiplied this, I would probably say, okay, that's 3x to the fourth, and this would be a 3x squared, a plus. But you see that these two don't line up, and so it becomes a little bit confusing. What are you supposed to add? What's going on? These are not like terms. Okay, so this is where you could actually cause yourself a big problem. But by putting that there, it doesn't change the problem at all. 3 times 0 is still 0x. X squared times x is x to the third, right? We keep the variables. We just put the 0 coefficient in front, but we combine the variables for organization. And then 3x squared now goes below the correct term. Subtract. That doesn't matter. It's a 0. This turns to a negative. These two cancel. That's good. This turns into minus 4x to the third plus 9x squared, and bring down the 0x. Again, these zeros just for placeholders to be sure that you don't make a mistake. Okay, divide. Minus 4x, multiply, minus 4x to the third, 1 there, 2 there, plus 0x squared, 1 from the top, 1 from there, again, just as a placeholder, and minus 4x, subtract, and we get 9x squared plus 4x, and bring down the 5. Last term is a 9, right? 9x squared divided by x squared is 9. These two degrees are the same, so I have to do one more step, and I have one more spot left over. Okay, so you can sort of usually tell when you get to the end here. And our remainder is going to be, yes, there's going to be a remainder. It's going to be a little bit weirder. Okay, so when I multiply this, I get 9x squared plus 0x plus 9, subtract, and I get 4x minus 4. The degree of the remainder is 1. The divisor is 2. The degree of the remainder is less than the divisor. You're done. You stopped. And my answer is the quotient plus 4x minus 4 over x squared. I don't need the 0 anymore, plus 1. And we write it as a fraction. Okay. Now, this one only had 1 zeros. We can do it with a whole lot more. Is x minus 2 a factor of x to the fifth minus 32? So x minus 2, and oh, whoops, I'm going to need a little bit more room up top. Why am I putting such a big line? Because I need x to the fifth, 0x to the fourth, 0x to the third, 0x squared, 0 x's, and then the minus 32. Okay, divide. Multiply x to the fifth minus 2x to the fourth. Subtract. So that's 2x to the fourth. Bring down 0x to the third. Divide. That's 2x to the third. Okay, multiply. That's minus 4x to the third. Subtract 4x to the third. Bring down the 0x squared. Again, this one is going to be a little bit longer. Divide. We have 4x squared multiply third plus, no, sorry, minus 8x squared. Subtract. Bring down the x. Divide. Multiply. 16x. Subtract. Almost done. Bring down the 32. And now multiply and subtract gives us 0. So it is. Okay. And my two factors were x minus 2 and that other big long one up there. Now, if you remember the factor theorem, right, if p of x is equal to 0, then that term is a factor. So for x minus 2, we can say if x is equal to 2, that is the root. Okay? We can say what is p of 2, and in this case it would be 2 to the fifth minus 32, which is 2 to the fifth is 32, so that is actually 0 as well. So this is a quick way to tell if something is a factor, but it didn't give me my other factor. Okay, so we needed to use long division to figure that out. So let's try that one more time. So x minus 4, so that would be x, or x to the fourth minus 1, x to the fourth minus 0x to the third minus 0x squared minus 0x minus 1. Is that a factor of x to the fifth plus 5x to the fourth, 0x to the third, 0x squared, minus x minus 5. This seems like it is long and crazy, but we can cut a lot of stuff off of this. Divide, because right, x to the fifth divided by x to the fourth is just x. So we're going to start right there. So we're only going to have to do this twice. So not so bad. So that's x to the fifth, 0x to the fourth, 0x to the third, 0x squared minus x, subtract, and we get 5x to the fourth, and then that's it, minus 5. And so divide, and we get 5x to the fourth, 0, 0, 0, 0, 0, and a minus 5. And so, yes, it does work. So this setup should be kind of familiar to this setup, right? Where we have this sort of same situation going on, where you see 672, 672 in there. Not that this would really be helpful to recognize unless you actually had a problem like that ahead of time. Okay, so it's going to be x plus 2 times 3x plus 1 would equal this polynomial. Remember I said there was a shortcut? So for long division, it's in the name. It's long, okay? I really don't want to have to do this unless I really have to. This is kind of a pain, okay? There is thankfully a way to shrink this process and speed it up, and it's something called synthetic division. And this simplifies the long division process for dividing by linear expressions. This is not a linear expression. It's x squared. So this technique would not work for this particular problem. But that's linear. It's x minus 2. So I could have used a quicker method to figure this one out. Okay, so to use synthetic division, write the coefficients, including missing zeros, of the polynomial in standard form. You are going to omit all the variables and exponents, and there's a picture on the next page. For the divisor, use the reverse sign, use a. So for instance, if I have x minus 2, the thing I'm going to use, and write this is equal to 0, the thing I'm going to use for synthetic division is the actual root, is 2. So you will have to reverse the sign. And this allows us to add instead of subtract throughout the process, which makes it easier. So here is a long division compared with its corresponding synthetic division. And the first thing I notice is how much less there is going on the right-hand side in the synthetic division. Okay, and let's go through all the pieces. Here's the divisor, x minus 3. So because x is equal to 3, that's what goes there. Here's the coefficients, 1, 4, negative 5, 5. 1, 4, negative 5, 5. Those go in that row right there. And then the rest is calculating the problem. We'll go through how to do that in a second. But you can see that we have a 3 there, a 21 there, and a 48 there to represent these, only they're the opposite sign, which is good. What we want to recognize, however, is that 1, 7, 16 is my answer. 53 is my remainder. Okay, so this is a way to condense all of the long division into 2 or 3 nice, easy rows of data. Let's see how it works. So first, use synthetic division to divide this by x plus 2. That must be linear. If it is not linear, if it is not x plus or minus something, it doesn't work. Okay, so the first thing I'm going to do is say that x is equal to negative 2 in this case. Okay, so that's what goes in this little box. Then I take all of the coefficients. 1, negative 14, 51, negative 54. And then I draw a line. Okay, the first step for synthetic division is to bring down the first coefficient. So I take this 1 and I write it down the bottom there. The next step is to take the negative 2 and multiply by the number on the bottom. So negative 2 times 1 is negative 2. And that goes above the line. Then I add these together. And now I repeat the process. Everything below the line gets multiplied by negative 2. So negative 2 times negative 16 gives me a positive 32. Add these together, not subtract, add to give me 83. Multiply, we're getting big numbers, that's okay. Add together to give me negative 220. So the way this works is you are dividing by a linear expression. You're dividing by x plus 2. This line is your answer. the degree of your answer, these are the coefficients, the degree of your answer will always be one less, because this technique only works by a linear divisor. So your degree will only go down by 1. So this becomes x squared, 1x squared, minus 16x plus 83. This last term, sometimes I'll go like this to really emphasize that this last term is the remainder. So that's minus 220 over the divisor. Okay? And now we have successfully divided this using synthetic division without having to make a big long division mess, pretty much. And this is actually much faster as well, which is going to come in handy in some of the next sections. All right, so let's try this. Ooh, be careful. Notice that there's a missing term. X squared is missing. We can still use synthetic division. I'm going to put a positive 7, the opposite sign here. But if I just do this, right, I'm going to get the wrong answer. I need to put in the 0. I need to put in the 0 for x squared. Put a line, bring down the 1, multiply, add these two together, multiply, add these two together, which is 8. No, sorry, negative 8. Multiply, and now that works, right? Well, sorry, this division, right? We always are able to divide, but now I know that x minus 7 is a factor of this term, okay? Which means that x squared plus 7x minus 8 is my other factor. Okay, here's where this gets really useful, is that we just had this expression, x to the third minus 57x plus 56. It had no common factors. I couldn't factor it with grouping. There was no way I could go about factoring this expression. Now, however, now that I've divided this piece out, I did it using synthetic division. I could have done long division if I wanted to, but I divided it out, and this is what's left over, which can now factor using my regular quadratic techniques, which means that if I wanted to factor this whole expression, it would have been x minus 7, the first term, x minus 8 times x plus 1. And I've now got all 3 factors and all 3 answers of this cubic trinomial. Very useful, coming soon. Let's try another problem. Weird word problem, but not really too bad here. The polynomial x to the third, blah, 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 expresses the volume in cubic inches of the shadow box shown. What are the dimensions of the box? Here is the width. So all I have to do, if the area or the volume is this thing, I divide out one side and I see what's left over. So let's divide that out. So I'm going to use synthetic division because it's linear. I'm going to put the opposite sign in the little box here. I'm going to put my coefficients 1, 7, negative 38, negative 240. Put my line, bring down the 1, multiply, bring this down, multiply, negative 48, and negative 5 times negative 48 is 240. So this works, okay? The leftover polynomial is now 1 degree less, x squared plus 2x minus 48, which can then be factored to x minus 6, x plus 8, okay? Which means that the length, the width, and the height are x plus 5, x minus 6, x plus 8. And it says the length is greater than the height. So this is the length, that is the height. Sorry, other way. Sorry, other way. The length is greater than the height. That's the length. That's the height because it is big. Very good. Okay, and then if we had a specific number, we could just plug them in, which is what the next part says. All right, so let's finish with something called the remainder theorem. The remainder theorem provides a quick way to find the remainder of a polynomial. Why is that useful? Because if you divide a polynomial by some factor, then the remainder is P of A, is the function evaluated at that point. So this works because here's my long division algorithm, right? Divisor times the quotient plus the remainder is equal to the original polynomial. So if you're plugging in this factor, whatever it is, x minus a, right? And now you plug a into this expression, right? The quotient cancels out, and it's just the polynomial is equal to the remainder evaluated at a, which is usually just the remainder. Okay, so what this means is you could take 3 and you could plug it into all these numbers in order to get an answer. Or you could use synthetic division, okay? Or synthetic substitution, this is called. The difference is that is what, right? This is x is equal to 3, so I don't have to change the sign, right? That is what goes into the expression. So that goes into the box. I put a 1, I put a missing 0, put a -2, put a -1, I put a missing 0, I put a 2, and what I'm looking for now is the remainder. So P of 3 is going to be equal to whatever is in that circle right there. Add, multiply, add, multiply, add, 180, 182. Okay, so the answer, P of 3 is 182. And yes, you could have raised 3 to the 5th power, subtracted 2 minus 3 to the 3rd. The problem is that if you had to do this on sort of a standardized test, maybe off the top of your head, you're really not sure that 3 to the 5th power is 243. Okay, so maybe you might want to use this method instead of something else. Okay. Try one more of those. So -4 goes in my synthetic division box. There are 5, 4, 3. Ooh, look, I'm missing a 2. Okay, so 1, -3, -28, 0, 5, and 20. And let's see what we get. 1, -4. Combine those to get -7, which is a positive 28, which is 0. Multiply is still 0. Add is still 0. Multiply is still 0. Add is 5. This turns into -20. And we get that P of 4 is equal to 0, which means that x plus 4, right? The opposite side, if x is equal to 4, if I set it equal to 0 to get my factor, we get x plus 4, or if x is equal to -4. This is one factor of this expression, which is not really what they asked, but it's good to know. Here's the rest of the expression. Maybe there's some other techniques that we can use to factor this more in order to get every single factor, all 5 solutions of this expression. And that is coming next time. Okay. So real quick, all of these questions right here, every single one of them, I would divide using synthetic division. It's faster, it's shorter, and the only confusing part is to make sure you put in a missing 0 if you have one, including at the end, like number 5. Now, you cannot use synthetic division, right? You can only not use it if you have a nonlinear factor. that is a linear factor. But if it was something like that, I also would not use synthetic division because it becomes much harder. Because now you have a fraction in synthetic division, and it makes the problem much, much harder. Okay? That was section 5-4, dividing polynomials.